Today is assembly day. I want to build this high torque, low RPM gearbox. This is a Chinese product. I bought it from AliExpress for probably for a couple dollars. I want to model this idea into FreeCAD. So I will focus on how to build this, put this together in assembly in today's video. You can see there are 4 pairs of gears, large and small. They are assembled in such a way the torque will be enhanced by a lot, but the RPM will be reduced by a lot as well. I have FreeCAD 1.1 installed on my computer. FreeCAD 1 version had assembly workbench integrated into it for the first time. However, it had some problem in it. More gears would slow it down, and then it did not have this simulation capability. And I would recommend you to start using FreeCAD 1.1 if you are interested in assembly. So let me take a couple minutes to explain how I build these parts, and then I'll be getting into describing in detail how to put this together in the assembly workbench. These are the main components that I use to build this model, build this gearbox. I have 4 pairs of small and large gears interlocked to each other. Before I get into the interlocking things, let me show you real quick how I build these gears. So as I mentioned earlier, I used gear workbench, and here you have involute gears, different kinds of gears, but mostly we'll be using involute gears for this build. Let me open up a new file. And building a gear is very simple. I have other videos explaining detailed process of involute gear, so I'll put those links in the description of this video below. But very quickly, this button, the first button on the gear workbench says involute gear. You click on that, you get in involute gear. And let's talk about a few properties. We will mostly deal with the base properties. The first one, it says height. You can update the thickness. And then next it says the module. So you can change the module to a larger module, a smaller module. And then you can have different number of tooth in that gear. So as you notice, there is no diameter in this gear input property list. Now that seems a little bit weird if you didn't know anything about gears. It's a circular shape, almost more or like it's a circular shape disk, but it doesn't have diameter in the input area because we have the module, which is the most important parameter in the gear, in the world of gears. Module is a ratio between the diameter and the number of teeth, and that's why you either input module or diameter. Now, number of tooth, you cannot have 2.5 number of gears, right? It will have to be either 2 or 3 integers, and that's why number of tooth is definitely a input. And then module can be integer or fraction, so that is also very important, and you can input that. So a higher module will give you a larger diameter of the wheel, the gear, and then a number of tooth, you can adjust that. These two will determine which will be the pitch diameter. So pitch diameter is always a calculated property. You can get that from the computed section. In here you have the DW, which is a calculated. You cannot input the diameter as in this format, right? So if you wanted to go with more number of teeth, you can do that. You can go with smaller module, which actually squeezes the size of the tooth size. So a larger module will give you a bigger size of the tooth. Smaller module will give you smaller size of the tooth. One thing we'll have to remember is, like, if you are trying to couple one gear with another, those two coupling gears must have same module. You cannot couple one gear of 1.5 to another gear of 1, for example. You cannot do that. So in my setup, I kept all of those gears of the same module. For example, we get into this, and this gear has 7.5 millimeter diameter, but the module is 0.25, and all of the gears in this setup is the same module 0.25. So I didn't have to worry about a different module. I always worried about number of teeth. So number of teeth makes it a bigger wheel. Number of teeth makes it smaller one. All right, one more thing in the gear workbench. So you select the involute gear, and if you wanted to have a hole in the middle, it is very simple. You go to the hole and then select Excel hole, make it true, and that will show up. Well, it's not showing anything because the default diameter, it says 10 millimeter. Let's make that 5. Yeah, so that's there. We can have a different diameter of holes in there. So that's what we did, all my gears in the gear workbench. And then I build this shaft using part workbench and put them together. For example, this first end, that's 1 unit. And this one has a gear and a shaft. So there is the gear and there's the shaft as a circular extrude. That's all about how I build this model. And now let's jump into assembly workbench. Assembly workbench is a built-in workbench that ships with FreeCAD 1 version. It was not there. So if you are using a 0.21 version, for example, or like a previous version of FreeCAD, you will have different other workbenches that you can install on your computer. But the default assembly workbench is started from FreeCAD 1.1 version and later. So assuming you have FreeCAD 1 version at least, I recommend that you start with FreeCAD 1.1 because it has better assembly setups in there. Let's go ahead, close out our previous test file. I don't need that. And what I want to do, I want to hide all my parts. And then start an assembly. As soon as you start an assembly, it is always activated. So double clicking on it deactivates it if it is activated, or activates it if it is deactivated. Or you can right click on it and then see if it is active object or not. All right, so we will have to have this activated all the times if we want to work anything on the assembly workbench, just like for design bodies. If you want to work in that container, you will have to have it activated. So if you close this file in the middle and then reopen after some times, be sure to activate your assembly before doing any kind of work in there. All right, now that we have assembly container created, first thing is to insert parts. And here, once you click the insert button, you will see all the available parts that's available to be inputted in this assembly. Now you will notice anything open in this left panel, even if you have a different file in there, different FreeCAD file, those files, those parts will be available for your current assembly. So you can have a different file, right? And then you can insert those parts in this assembly as well. Luckily, we have only same file open, but we have 8 different parts that we'll have to insert in there. So let's start one by one. Now you can see all the available parts are available in here, and then those parts I can go by the name and then recognize it. It is very important to recognize those parts by the name that you provide. So if you have extrude 001, extrude 002, extrude 010, that might not be the best practice for assembly workbench. I would recommend always rename your parts and sketches so you can go back and actually see which one you are trying to edit or try to work on it. In here, the first part that I will be adding will be the support system, because anything that I add for the first time, it will be grounded, it will be fixed in place. So I want to add, say, first end is the motor end, and I want to add the end plate. So let's add the end plate. And if this is the first time you are working on the assembly workbench, it will ask you to, if you want to ground this part the first part. I said yes for all the time, so it is grounded. So you can go ahead and ground this part. If you'll notice, there is this lock, that means it is grounded. And on this first end, I have a bigger hole, that's the shift end, and this is a smaller hole that will hold the companion gears in there. So that is my first end. And while I'm here, let's go ahead and add the first end, which is the shaft containing the smaller gear. And now we can see that without clicking anywhere, you are given the option to move things around with this axis cross. So you can do that. You can place your part at a suitable location, or if you click somewhere else, that axis cross will be gone, but still you can drag that part, which is free moving in this environment. We're still in that insert component phase. If I want, I can add another component, right? But I don't want to right now. I probably next time I'll show it to you. But what I do is first time I always add the ground part, and then I keep adding one by one. I don't like add 4 or 5 different things at the same time and then get confused later on. So it okay. Now we have this part is fixed. You can get into the joint list and you can see the ground joint. It is fixed in place. I'm gonna hide that. And this one is free floating. What I want to do, I want to put this shaft in that hole, but it will be revolving all the time. So that joint will be Revolute Joint R. So take that. And now it is important to click where you want to. I want this gear to show up on this end. So this edge, I want that edge to be mated with this edge. So it is important to select the edges, and that way they are in place. You can give it a try. So you can use the mouse gesture, drag, and see if it is working. It's working. And that's all. Very simple. The Revolute joint is very simple. Now we have here. So it is important. Say if you did not click the right circle, it will be offsetted, and then you'll have to apply additional offset to bring it into place. All right, so first part done. Let's go ahead and add another part. We will add the thing right here, the companion gear right next to the first end. So that would be first companion there. And we can move it up and hit OK. And I want to put this smaller shaft into this hole. So I will do, what I'll do is like, I will do what I'm not supposed to do, so that you can see how you can correct yourself if you did something that you didn't want to do. So I click on the Revolute joint, and then I want to select, so I'm supposed to select this end, right? But say I selected this end on this side, and then I selected that mating circle in there. You will see that the gear is sucked into the plate, right? So I'm not supposed to do that. But if that has become the case, like, there is no other way for you to actually do something like this, you can always offset the gear. You can make it a offset. So there, something like this. So I think it's a 1 millimeter thickness. So -1 works for now. I can leave it like that, or I just can correct it. I do it like correctly. So select that edge and select the circular edge on top. Makes it very simple. All right, now we have 3 gears installed, and I can see that this is moving, this one is moving, but they are not biting each other. Like in reality, they would be biting each other. So if I wanted to rotate this one this way, this will be rotating this way as well, which is not doing because FreeCAD does not have object collision detection, something like that. So it will not know if there is a tooth or not unless we tell it so. So what I want to do, I want to drag it with a good fit. I think that's a good fit. All right. And now I want to apply a gear joint. All right. So I know that I'll have to come back. I cannot finish this gear joint right now, but I want to do that anyway, so you know what to do before you jump into there. So click on the gear joint and then add the gear. So we want to add the gear, or we want to add the surface that will show the axis of the gear right now. So this whole thing, the both of the gears has the same axis. So I can select this circular surface. It will still work fine because that's where the Z axis is. So select that surface and select this surface, not here, not here, in the middle. We care about the axis, so there. And now it is asking us for radius 1 and 2. So if it is radius 1, supposedly this will be radius for this gear, this big gear that we want to couple, and we don't know the radius. And the radius 2 will be radius for this smaller gear, and we don't know the radius. So let's go back. Now, so this is the first end. I want to go in there, first end. Click on the involute gear, get into the property. We want the pitch diameter, which is double the pitch radius, so 3.75. Let's take that and say 3.75 millimeter. And another one is the first companion. That's what we added. And this radius, there are two radius, two gears. The first one, it has a DW of 6.25. Another one has DW of 3.75. So obviously we are looking for the bigger one because that's what we are coupling. So take this one, 6.25. That's what we are looking for. 6.25 millimeter. All right. Now we can get back to the assembly. It is still activated. And what we want is get into gear joint. And again, select this surface. Axis is important. And select this surface. Axis is what we are looking for. And the first radius would be 6.25 millimeter. And this one will be 3.75 millimeter. All right. Now I can leave it like that. Although these are diameters, it will be ratio that is calculated in MIDI. So for this specific case, you just can provide two diameters. Just don't mix it up, like provide one radius up here and another diameter up here. No, if you are providing radius, both of them should be radius. And if you're providing diameter, both of them should be diameter. And hit OK. Now the gear joint is right here. You can select that and hit space on top of it. You can see what are the two components it's marrying. And theoretically, if we move this one, oh, it is moving right. So if I rotate it clockwise, this one will be rotating counterclockwise. If I rotate it counterclockwise, this one will be rotating the other way. So the gear works, like gear joint is working fine. Now I want to go ahead and start a simulation so I can check it every time I add a new gear into the system. So go in there. Now I want to add into the motions, I want to add the Revolute joint. So I have two Revolutes. The first one is the one that I added right here, and second one is the Revolute on here. So maybe I will use the motor side and just leave it at default like that. So one of the Revolute joints is added right there and hit generate. Now we can play. I can see that so far our gear is working fine. You can hit OK and you will see that simulation is added on our materials list. This will come in handy. We can go back in there and then double click on the simulation and then generate and play. So this is one way to check our work. All right. Okay, now let's move forward. We want to add another set of gears right here, and to do that we'll have to have the supporting plates. So what I will do is I will add the border there. It's on the other side, so we'll probably add it like that, right? Hit OK. So the border, we'll just fix it with this supporting plate. So what I will do, I'll just fix it. So for a fixed joint, I want to bring this edge right on this edge. So on the fixed joint, it is important which one you are selecting first. So I want to select the edge that is fixed. It's right there. And add the second edge, which will be moving down to that edge. And that's one fixed joint is perfect. We don't have to fix this part as like we don't have to do that. Okay. So that part is fixed. You can drag that part, see it is fixed. And that should not affect our simulation. It is still the same thing. That fixed part should not prevent this one from moving. All right. And let's keep adding. So we will add the mid plate. You will notice that mid plate has 3 holes where the end plate had only 2 holes. The middle hole is the same shaft diameter and 2 smaller holes to hold. So this one will hold this smaller end, and this one will have another companion in there. Now for this one, I can just place it in there as a fixed joint. This is working fine, but in reality you would want to have a gear joint, like a revolute joint with this one as well, so there will be another bearing. But in FreeCAD, that will create a redundancy. So if you have a revolute joint on one end and another revolute joint on the other end, in FreeCAD's mind you are over constraining it. So if you come across scenarios like that where you would have 2 bearings on both ends, I'd recommend just add 1 revolute. It will work fine. But if for peace of mind, if you wanted to have another end with some joints in there, how about a cylindrical joint that will open up the lateral restrictions, but it will have that revolution in there. So let's see if we can add a revolute joint right there, a cylindrical joint. So it is the revolute joint minus the lateral movement restrictions. All right, so I'm going to go ahead and add this circle and this circle in the middle, right? And that's our cylindrical joint. So cylindrical, if it was a revolute joint, you could move it like that, but because it's a cylindrical joint, it will move up and down and rotate as well. So this is not over constraining, it's just rotating. All right, now it is rotating. Let's move it in place and apply a fixed joint between this edge and this edge there. Right, now we have added another joint with our previous system, so I'm going to go ahead and verify our work, if it is still moving. It is still moving. All right, so we did not over constrain. One of the previous videos that I did, I'll leave that link in the corner right here. You will see that over constraining these assemblies kind of like messes up our setup, so the assembly doesn't play good. Now that it is playing good, I think we are safe. All right, let's move on. I want to add so we added the mid plate. I want to go ahead and mid coupler would be the next one to add. This will be coupled with the smaller gear and also be supported with this gear in here with the mid plate. I want to make that mid plate connection first. So that will be another revolute joint with this. Let's take this surface and maybe this edge. Perfect. And okay, so revolute joint is very simple. I like revolute joint. I mean, I don't hate any joints, but revolute joint, I kind of like it. All right, now we'll have to apply a gear joint between these two. I believe I kept the ratio same. So if it was 3.75, the small one, it's worth double checking. So we go in there, the first companion, and the first gear was 6.25 millimeter radius diameter, and the second one was 3.75. And this one, mid coupler, we have 6.25 as the, so 6.25, 3.75, the ratio is the same, we can use those two values. All right, let's go ahead and apply a gear joint between this axis and this axis. So we are selecting the axis, but when we apply, oh, I should have, all right, position it first. Let's go back. I want to position it first, right there, and then apply the gear joint. Otherwise, it will not look pretty. Right, this axis and this axis. So the first axis would be smaller gear. The radius is 3.75 and 6.25. Looks good. Hit OK. Now this should work. So go into simulation. Now you may think I'm being paranoid, checking every now and then, but it is very important that you check your simulation every step so you are not missing anything. All right, so far it is working. Let's bring back our mid plate. It was right here. There. So the lower box is working fine. Now that we have translated that low RPM in the middle, let's add something right here. Add another component. So as I said, we can add two different parts or like multiple different parts at the same time. I'm going to go ahead and show that. So we added one, and we can add, say, another border. Yeah, why not? So we added two components. So now in the system, we have two floating components, right? Maybe I want to fix this part first, or just leave it like that. We can come back to that. So the work is pretty much repetitive right now. We are adding this end into here, and then positioning it. Moving this one is much easier because it is free moving. All right, that's good enough. All right, I think I built in some clearance right here. I didn't do that. So these are they do not have any clearance, very tight fit. I tried to do that on this one. Cool. Okay, now that they are positioned right, I will apply a gear joint between this surface, well, this axis and this axis. And so the bigger one would be 3.75 and 6.25. Let's see how good is my memory. As long as they are not biting into each other, they are working fine. Those values, I'm gonna say those were the right values, the radii. All right, that part is working too. Now let's go ahead and put this border. So take a fixed joint, take this edge and take this edge. Very cool. And while we are adding the box, maybe add the end plate one more time. So you will notice that this end plate is the same end plate that we added. So in the assembly, we don't have to clone before we get into the assembly. We can reuse different parts. So this border, we reused it. This end plate, we are reusing it. But the hole is in the different place. We want this hole to be on this side. So what I will do is I will take this cylindrical joint and add that hole first. There. Now it is going up and down, rotating. Right? Now I can go ahead and fix this edge to this edge. Perfect. So we have our box. The only thing left is this output shaft with a gear. Right. Now this part is fixed, but let me hide this for a minute and bring in the slow end. All right. Maybe I need my end plate to fix it. So this one, all right, I will be applying a Revolute joint. So I selected the lower edge and this circular edge. Pretty good. If I remember correctly, I have a different gear ratio between these two. So 6.25 and 3.75 is not going to work here. I have. So let's go ahead and check those values. Put them right there. And what I want to do is I want to get into the slow companion. Go to, so this gear has 2.5 millimeter. I believe that's what we're looking for. This is going to be 2.5 millimeter. And this bigger one, we want to go check it up. Let's see what is the DW value. 7.5 millimeters. So this is further reduction. So we have a smaller, even smaller wheel compared to the previous ones, and even bigger wheel. So the reduction will be much more at this level. All right, we have those two diameters. Let's go ahead and apply a gear joint between this axis and this axis. Although, if you'll notice, although I have different number of teeth between this pair and this pair, the axis is actually on the same level. The distance, the horizontal distance between these two axes is the same. I kept that axis length same so I could reuse this plate on the other side, but I just wanted to have different number of teeth between these two. All right, so the first one, I think I selected the slow end second. So this is going to be 7.5 and 2.5. Right, hit OK. Moment of truth. I want to go ahead and get into my simulation. Double click on it and generate. You have to generate each time you want to play it. And play. And play. All right, something happened. It's not working. All right, let's take a look at it. So this is moving. So the system is moving, just the simulation is not working. Yes. So maybe I will have to create another simulation. Let's go ahead and delete that. All right, that is unexpected. All right, so let's go ahead and create another simulation. I want to add the first revolute. So there are like multiple jointers. I want to keep the first original revolute. That will be where we will be applying the motor torque. Hit OK and generate. Oh, it is working. So it was probably a fluke, something. So you can see this end is rotating faster and this end is rotating slower, much slower. All right, maybe I want to make these transparent. BT on the keyboard makes the thing transparent. And now let's play it one more time, just to make sure we have things in place just the way we want it to. All right, and my target would be to have a full revolution. Doesn't look like it's doing a full revolution. It's skipping, so maybe I will increase this timing to 1.2 and then generate. Now looks like it is doing a full revolution. I wish on this simulation setting we could, so now we added a revolute joint, right? And I wish we could say that joint we want to rotate it full 360 degrees. So in addition to start and end, these are the timing. I wanted to see if there is the degrees. I want to rotate it 25 degrees like a stepping motor or like a full 360 degree rotation. and that would be a fun thing to do. All right, for now this is working perfect, just the way we wanted it to. And I want to add the end plate. Awesome. Now if you remember correctly, we did not apply that transparency to this end plate. It was this one that we applied, but because these are the two the same thing, the transparency was auto applied. What I did in the previous trial, I applied different colors. So let's see. I want to apply maybe a random color to it. Oh, that didn't do it. All right, let me save this before I do something stupid. Let's go and say fast end, right click on it and apply random color. It worked. But if I want to do it from this side, say slow end, random color, and it's hidden, which should not be. The Control Z, let's bring that back. Okay, so if we want to add color, I'm sure this is a bug. They will fix it pretty soon. But if you want to apply different colors, for now, do it from this part list. Okay, so I wanted to apply these colors just to make sure the illusion is we have the same shaft going through. However, I wanted to just make a distinction that the shaft is disconnected right here. So between this gear and this gear, there is no connection between there. Like here, it is evident between this gear and this gear, the shaft is supported by the mid plate. They are not continuously running through. So the shaft is broken right here and right there. So the power is flowing through this shaft, taking a left turn, going up, taking a right turn, going up, taking another right turn, going up, coming to the left, and finally goes to the output shaft. So this is the flow of energy through this system. All right, and that's the end of the assembly. I wanted to show you how much reduction, how much total gear ratio this system is producing. So I want to do that through an online resource. Here is this web page. I will leave this link in the description, or you can see it. So this one has the system that we just built. It has a similar calculation system. So there is the in, and then we'll have to apply the number of teeth. So let's go ahead and do that. Input speed, let's say 2500. So this is the variable. And number of teeth, we want to input gear, and I want to put it side by side. So input gear, this one first end, the number of teeth is 15. So there, number of teeth is 15. And number of teeth in the gear 2, 25. And I think that goes, and this says on the same shaft as the input gear, I'm going to say no. So the next one will be this gear, which is 15, the same. And then this 15 is connected to this 25. So on the same shaft as gear 2, we'll have to say yes. And we are going with 2500 RPM. Let's see. So it says the combined gear ratio is 0.0720. If we apply 25 RPM, 2500 RPM in there, it will be output speed will be 180 RPM. If you apply 100 Newton meter torque and the gear ratio, divide that by gear ratio 0.07, so the torque will be like massive through this system. All right, my friends, I hope you enjoyed this assembly. I wanted to focus mainly in this video on the assembly and then simulation capability of this FreeCAD. But if you have any question, comment, or suggestion on how to build this model, building these parts in part and part design or gear workbench, please let me know in the comment section below. I'll probably do a better detailed video on how to build different parts, keeping the assembly workbench in your mind. Thank you for watching. I will see you in one of my next videos then.